Okay, so we're talking today about hypothesis testing with SAT tests. So let's recap from last time. Last time we characterized the normal distribution curve utilizing the mean and the standard deviation to define so-called SAT scores. So basically the definition of a SAT score, of a standardized score, a standardized value, is the distance of an individual score from the mean expressed as the number of standard deviation it's located away from the mean. And this is important because this process of standardization allows to compare individual distributions of different variables with a different metric, a different magnitude, a different distribution against each other. And that is important in many contexts. So if you remember last time we looked into emotions and the emotion of fear and disgust over time in a time series plot. And the comparison of that in terms of SAT scores basically shows them standardized as per the population average at each year. So it basically allows a fair comparison between these emotions, irrespective of the magnitude of the assessed value. So that makes it very useful and very helpful for many analytic procedures that you will see now in hypothesis testing. That will be important for the ANOVA, that will be important then for regression and correlation as well. So all analytical procedures kind of based on the same principle, that you can standardize a distribution based on the standardization into a SAT score. So the SAT table, in addition to that, also gives you the percentage of scores in your normal distribution that are below a certain point, or they are, as expressed by Nolan and Heinzen here, between the mean and the given SAT score. Let's recap how that looks like. Don't forget how to read this SAT score table. So we have here on the rows, we have the actual SAT scores, including the first decimal. That means if you want to have 0.1 to 0.9 to 1.9 to 2.9 to 3 on the first decimal, this will always be the very last column in your distribution table. If you want to have more granularity and you actually want to look at the second decimals, you need to follow the respective row of the corresponding first decimal, and then it gets 2.50, 2.51, 2.52, 2.53, up until 2.59. So you basically follow this to the left and you get the increasing second decimal. And when you look at the numbers in here, so these are the actual proportions. So keep in mind, proportions is from 0 to 1, whereas the percentage is from 0 to 100. The difference between a proportion and the percentage is multiplying it by 100. If you have a SAT score of 0, that is your mean. So that's 50%. That means less than the mean, you have 50%, and greater than the mean, you have another 50%. That's the upper and the lower 50%. If you have the 25th percentile, and you can find this value by just following this following the actual percentages here. You remember the interquartile range is from the 25th to the 75th percentile. If you go here to the actual proportion, this is the 25th percentile at a SAT score of minus 0.68 and 7. So that's your 25th percentile. Equally with the 75th percentile, you find the same distribution here. If you find again your 75th percentile, that's again with 0.68 and 0.67, because it's symmetric, right? But that is only the case with a perfectly normal distribution. In a perfectly normal distribution, your mean and your median are also at the same spot. So is the mode. And the normal distribution is unimodal, only has one mode. So these concepts are important to keep in mind in this context. So in addition to that, it's also important to keep in mind you can always translate these percentiles also in probabilities. So if you say, okay, my entire population has a normal distribution, and I know less than my set score of 1.67 or say 1.68, minus, okay, now less than minus 1.67 would be 25% of my population. That means that if you draw a perfectly random sample, you have a 25% probability to draw an individual from your population that has an actual value, whatever that value is, you standardized, less than that particular score. That is also important to keep in mind, because we're translating today with hypothesis testing, we're translating these percentiles into probabilities. Good. Okay. So this was basically the basic of standardizations. We have discussed this in the last class. We will talk about this a little more today. So keep in mind that there is a conversion from a raw score to a set score, which is done by the individual score X minus the mean divided by the standard deviation. So you get this difference, and this difference you're standardizing as per the number of standard deviation in between. If you look this value up on your set table, you basically find the corresponding set score, and you find the corresponding percentage of individual that is lower than this entry. So that's what the proportion means. You find an individual set score, and the proportion means that this is cumulatively that population less than that value. That is very important knowledge to keep in mind. So yes. So if you have a proportion on the distribution table here, you go from set score of minus 1.22. You have here 0.1112. That means that 11.12% of your population have a value that is smaller than the corresponding score to minus 1.22. So if I convert this now, let's say we have blood pressure, what is known in the Einzelnen. Let's take blood pressure. So you have your normal distribution, and you have a blood pressure. The average blood pressure in the population, let's say, is 130. You have, the standard deviation is 10. So you come from 130 to minus 1, that's minus 10. That's 120. So minus 1 is 120. What the implication of that is now is that if you have minus 1, what's minus 1? That's now 14 and 2. So that's 16%, give or take 16% of your population is less than your set score of minus 1. That means if minus 1, set score of minus 1 is 120, that means that 16% of your population has a blood pressure less than 120. Well, yes, it's smaller equal. It depends how you phrase it, right? If you say greater, if you say smaller, then it's less than 120, or smaller equal, then it would be. So these proportions are also not very accurate, right? So you, for example, you wouldn't have really 60%, it's 0.1587. So this is rounded already by default. And in the end of the day, it's not really, this is not the most exact science. This is following a mathematical function, quantifying the area under that curve. So you basically have that function, and then you take an integral of that function, you get the area under the curve, and then you just split it accordingly. So you model this out, and then you take the respective segment that you're interested in. And a good question, thank you. So this knowledge of the percentages included under that curve, under that frequency polygon, below that threshold in question, is very important when it comes to questions that you will be facing on the quizzes and that you will be facing in real life, where basically you want to quantify two thresholds and you want to know what percentage of the population is in between those two values. And you can also utilize this to quantify the probabilities of being within that certain range. That becomes important with confidence intervals that we're going to talk about on Monday. So there is a distinction which I want to flag to you. So Nolan and Heinzen use a different distribution table. They are basically having a table that represents the area between the mean and the set and beyond the mean and the set. So it looks different. And I find this a little bit confusing, to be honest, but so what they're essentially doing is like they're taking, they're not showing 100%, they're showing 50%. They're showing 50% below and 50% above, which is a confusing approach. So I would not choose a distribution table of that kind. So I believe the one that I have given you is more intuitive. So you can now with these, yes. Mm-hmm. Yes, we talked about this. So this is at the individual X minus the mean divided by the standard deviation. That gives you the set score. Oh, yeah. Yep, that's the one from last time. And once you have this set score, then you can basically find the corresponding percentile. And this percentile allows you to quantify it, the proportion of the population that's below that value. And so now when you have the set score alone, and this is what they mean to, so you can either look up the actual percentage. So you can go and just find the percentage of 25 for the 25th percentile, then you find the corresponding set score, and then you just rearrange the formula and you multiply now the set score with the sigma, with the standard deviation, and you add the mean. That gets you to the individual actual score. So you can calculate this in all directions. And we have done this last time in the spreadsheet. So you can look that up on the spreadsheet. I have also posted it as an announcement. So this is obviously for many reasons, this is a very important exercise. And I agree here with Nolan and Heinzen. They are suggesting to take a piece of paper and a pencil and map out that normal distribution curve right in front of you when you're facing a question on the quiz. Because by that, you can visualize what am I actually looking at right now. Because if you just do it by your imagination, the imagination may play a trick on you. If you have, for example, you have to calculate the proportion of the population that is between a value that is a negative set score and the value that is a positive set score, it makes sense that you kind of mark it on a normal distribution sketch and you kind of, you support yourself how to calculate that now. And that is, again, an exercise that is easier with the distribution table that I've given you, because you just need to subtract two numbers. If you use their distribution table, you need to subtract 4 numbers, which makes it a little bit more confusing in my head. But basically, yeah, so sketching out the normal curve is a good idea. Stays clear memory, minimizes errors. It's a practical reference. It kind of gives you a visualization of what you're looking at, what you're dealing with, and it condenses information. Good. So keep in mind, you have the empirical rule, flagging this for the quiz. The empirical rule is certainly a question on the quiz. You have within one standard deviation to the positive, you're 34% of your population. One standard deviation below the mean, again, 34% of the population. You have within a set score of -1 and +1, you have 2 standard deviations covered, and that's 68% of your population. You go 2 standard deviations above the mean, you have 34 and 14, that's 48% of your population. You go 2 standard deviations below the mean, you have 34 and 14, again, 48% of your population. Ergo, if you go from -2 to +2, you have 4 standard deviation, that sums up to 95. It's not 96, arithmetically it's rounded, it would be 96, it's 95.7. But everything around 90, 96 is going to be fine. If you go 3 standard deviation, you have 99% of your population. So that's the empirical rule: 68, 95.7, and 99. So that's also important to keep in mind when you read research papers. You basically, you have a mean and a standard deviation, which is a standard form how these markers of central tendency and variability are being reported. You can, with one look at the table, you can say, okay, so that population that the author is presenting to me is approximately capturing 95% of the population if I multiply the standard deviation by 2. Above a sample size of 30. So that's, we're getting to that. Okay, any questions to that? If you use now that distribution table that I gave you, and you're being asked, I have a blood pressure of 130. I want to know now how many individuals are between a blood pressure of 125. So again, okay, so mean 130, standard deviation 10. Plus 1 is 140, minus 1 is 120. If you're interested now in the amount of the population, or the proportion of the population that is between 125 and 140, you know now that if you have this value, you have here 34 and 34 and 14 and 2. So you have 68, and that's 82. That's 84. So we have 84% was one standard deviation. So that's 140. Yes.
125 and 140.
Excuse me?
Please, how many are between 125 and 140?
Yes.
So it's 84%.
No, 84 is below your 140. So now the trick to calculate this range is that you need to have both anchor points, which is 140 and 125. You need to understand how much is below, and then you subtract the greater number, the smaller number from the greater number. Make sense? So you quantify now 140, which is plus 1. That's 84%. And now I need to know 125, which is 0.5. So that's minus 0.5. It's 130 minus sigma half, which is 10 divided by 2, that's 5. So it's basically, that gives me minus 0.5. And I know now, okay, so now I need to look that up. I didn't think that this is a nonlinear function. Yes.
Does it go like beyond like -3 and 3? Like, or it's just like, what if
it goes beyond? A good question. Thank you. This here is continuing into infinity. This is a function where which actually never reaches the axis. That's also important to know. So this will continue to infinity, and the decimals are going to get smaller, 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 and they go towards infinity and will never end. Agarn, I think you were first. Can you?
With every experiment. Like, how is this right for every experiment?
Because the calculation is always the same. You always calculate mean. No, you calculate x, the individual score, minus the mean divided by the standard deviation. So you're standardizing it in a format that no matter what variable that is, this principle will always follow the same. And that function is always the same. And the function always includes mean and the standard deviation. So it is a generally applicable rule to the normal distribution, irrespective of what parameter it is. And that's the fascinating principle behind it, that you can actually utilize this for whatever variable you're looking at, given that it's normally distributed. And that's the universality of statistics. You can use this for every walk of life, for every use case that you have. But great question. Thank you. Yeah.
For that example, why are you including the second 34%? Why are you including from 0 to 1? Why aren't you just including the from -1 to 0? So that's 34, and then -2 to -1.
Excellent question. Thank you. Excellent question. Because You have different ways how you can approach this. And this is really your freedom, how you want to do this. I'm giving you what I personally think is the easiest way, and that is to calculate the proportion less than this from the set-score table, because that's one value. Then I calculate here 0.5, and I know how much is less than that. That's the second value. And then I only have to subtract this proportion from that proportion, and I know what's in between. You can do it in various other ways. You can calculate it from the mean. You can actually say, okay, so this is this, and this is this, and I can add it up. So there are various ways how you can approach it. Conceptually, I think my approach is the easiest, but again, it's up to you. So there are various different ways that leads to the capital of Rome, as Roman literates have said in Latin. So so there are various approaches to that, and none is wrong. Well, it can be wrong if you do it wrong, but I mean, you can get to the same end result in different shapes and form. And that is what Nolan and Heinzen actually wants us to look at today, and that's why I'm showing this. Because you essentially, you can always assume that this is always 50%, and everything exceeding the mean, that difference is basically in addition to those 50%. The only difference to my distribution table, well, not my distribution table, the distribution table that I provided you with from Open Intro, is that it gives you that entire proportion up until to that set score, which makes it, I believe, easier and saves you 2 additional calculations in between. So conceptually, I think it's easier. So this is the simplest form. So you have a positive set score. You're just calculating the set score from your raw score. You get to the set score, you know what percentile this is. What proportion of your population is less than that. If you want to know now everything that's greater than that value, so you know now this is 84% or 83.65%. So this is 33.65 above the mean, plus 50, that's 83.65%. If I want to know now what is greater than or greater equal than this value, the only thing I have to do is I calculate 100% minus the 83.65, and that's 16.35. Yes.
So what was the answer to the blood pressure?
Well, let's finish that. So we have 140, and the set score of +1 we have here was 84.13. So that's our 84. If we're going now to minus 0.5, because we said 125, 130 is the mean, 10 is the standard deviation. Half of that standard deviation gives us minus 0.5. That would be corresponding with 0.385. So now I'm calculating 0.8413 minus 0.385. And that is somewhere in the ballpark of 50%. So in between is 50% of the bulk of the data. Is it actually? Oh, it's actually 53, sorry. Okay, so this is how you would approach this. It's simple, right? As a concept, it's just sketching out the normal distribution graph will make it a little easier because you don't trip over an oversight or a thought process that was incorrect in the moment. And there's also there's the quiz situation. You still have 30 questions to go. You may kind of just make a unnecessary oversight. That's why sketching out that normal distribution graph certainly makes sense. So you have different approaches to that. If you want to know everything that's greater than your value, you basically assume this entire function to define 100%. The whole normal distribution graph is 100%. You're subtracting now everything that's lower from 100%. You know what's greater. That's the fraction, that's the proportion of patients here, of the population that's greater. And now you have an additional aspect. And this will become important today for hypothesis testing, because you not only have smaller and greater, you also have, from a distribution that is symmetric, you also have the extremes, You have the extremes, extreme values. So if you're interested to have now, what is my probability that my that random sample participant or that random participant is outside of the range what I consider normal. I need to first calculate what is normal, and that's where the bulk of the data is, right? So you have in here, you have 0.98, that was, what did we say? 16.35, that's 32, that's 32.7. 100 minus 32.7 is 76, 70, no, 67, 67.3. 67.3% of our data is between a set score of 0.98 and minus 0.98. So that's 63.7% of our data. So now I want to know what is more extreme than these two thresholds of minus 0.98 set score or plus 0.98 set score. And that I do by calculating 100% minus 63.7. 67.3, not 63.7, 67.3. That is when you're teaching at the end of a long day, you basically start messing up. Okay, so you want to have now 100 is the entire curve, that's everything in the universe, minus 67.3, that gives you 16.35 from both sides because it's symmetric. And that becomes important for hypothesis testing because you want to look at probabilities, but we'll get there. So this is clear, right? It's considerably simple. So if you want to calculate scores between the means, so that's Manuel's height, you have negative set scores. So Manuel is a little shorter than the rest of the class. Here's a set score of minus 1.82. If you want to know what proportion of the population of all students in a secondary school is smaller than Manuel, and you calculate Manuel's height as minus 1.82, you basically will know that 3.44% of the population is smaller than Manuel. So that also can be done in the opposite direction. You can say, okay, so what proportion of my population will be taller than Manuel? And that is, you guessed it, it's 100% minus 3.44. Same exercise, just in the opposite direction. If I want to know who of my population has heights that are as extreme of an outlier as Manuel, or those that are even shorter than Manuel, and I take this distribution and like, who has values or who has heights that are as extreme as that of Manuel, I basically have a symmetric distribution, right? I have two tails. I look at this tail, I know it's 3.44. Given that it's symmetric, I can just flip it and I have the mirror image to those that are taller than this extreme value of a set score of 1.82. 3.44 multiplied by 2 is 6.88. And that is the probability of finding individuals that are as much of an outlier as Manuel, and those that are smaller than Manuel. And that is the concept which will lead to hypothesis testing. Any questions? It's considerably simpler still, right?
You just reiterate how you calculate the height. What you do get the proportion? You're given the height and you do that over the total.
Yes. So if we have 1.82, so this is calculated from an individual height. So let's say, okay, let's.
That value. You started off with 1.82.
Exactly. So you get a kid and you measure that kid, and that kid has a certain height, and so it's like, let's say it's 5'2", and I'm comparing it to the rest of the class, and the rest of the class in average is 5.5. Yeah, 5.5. I think it's 5 foot, 5'3", 5. you calculate based on that mean of the class or of the school or of all students in the US at that age. You calculate average height. Then you calculate manual in reference to that mean height and that standard deviation. You do need either, you need a mean and a standard deviation. And that is the basic requirements to conduct the SET test. You need to understand the population. You need to understand what's the mean, what's the standard deviation in the population. That will prompt you. When you have that given, think of SET test. Recognize it. Yep.
Last call, since you just talked about like the score, is there a difference between a SET test and a Z-score?
Yes. So the SET score is basically so the SET score is basically the score that is calculated based on a distribution on a given mean and a given standard deviation. The SET test is basically utilizing the concept of standardization with a given mean and a given standard deviation for a population to conduct hypothesis testing, which usually involves questions like, I have studied, and we will get to that, I have studied 20 individuals that were randomly sampled from a population. My population mean is 5.5. My population height is 5.5. My standard deviation in the population is 2 inches. I have now my sample with a mean of 5.3 or 5.2. And is my sample mean of 10 students, 20 students, 30 students significantly different? Is that different from the population mean? Under the null hypothesis, you will say, no, it's not different. And under the research hypothesis, you will say they are different. And then you're testing that null hypothesis of there being no difference. And you're basically getting, in the end of the day, you get a probability based on this concept of the SET score that the sample was actually drawn from this population and is not different, not significantly different. You will need to do a Z-score calculation based on a distribution of means, and we're getting there. So that's now the next step. It is the SET score of the difference. So you, I want to go step by step to get you there, because what you do in the end of the day, you calculate the difference between the sample mean and the population mean, and you assume that this sample mean and the population mean is the mean of means of a distribution of means. And you're saying, okay, so if I have this mean with that sample size, I assume that there's a variation around that mean that distributes with a certain shape, and this is where the standard error of the mean comes into play. And I'm standardizing, I calculate the SET score, I standardize the distribution of the means. And then I assume that my mean from the sample is actually identically or different from my population mean. And we're getting there. It's a little bit more tricky than just calculation of a SET score, but it is standardization of a distribution of the means. Yes, I'm just, so I have, yeah, so I have studied English in Europe. So I was told this is a SET. After I moved to the US, I was told that I'm pronouncing the C's and the C's. Yeah. Okay. Yeah, that's an accent thing. And I'm practicing hard to not lose my accent. So, okay, so we have now values that are as extreme as these two thresholds. We have 1.82 minus 1.82. We have every SET score less than that basically sums up to a percentile of 3.44. If I look at a mirror image of that above for the positive SET scores, I get the same proportion greater than 1.82. So you need to think of it symmetrically. Funny little example. Think about it. When you think of symmetric, if you sum all the numbers up between 1 and 10, what's the number? when you sum them all up? No, you sum all the numbers, including 10, from 1 to 10. You sum them all up. What's the sum of these numbers? Very nice, very nice. It's 55. What would have been, so how did you do it? Did you sum each individual? So there's a different way to do that. And the inventor of that distribution curve came up with a better way to do that. When you have 10 numbers that are symmetric in its appearance, you add up 1 and 10, that gives you 11. You add up 2 and 9, gives you 11. You add up 3 and 8, gives you 11. So each of these pairs on both sides of your list of numbers adds up to 11. If you create these pairs, that's 5 pairs. And you have 11 multiplied by 5, that's 55. If you do the same exercise with 100, same story. 1,000, same story. This is true for all numbers because it's symmetric. And that is exactly what we're looking at here, the symmetry. You really need to think about this in much detail to get to the bottom of this and then to kind of embrace that, because we will work with this quite a bit. And you have symmetric, you have a symmetric presentation of these extremes. So, okay, values that are as extreme as what you're seeing here. Why is that important? Because you're basically trying to understand percentiles and you try to understand distributions. I'm not really sure whether it comes into play here, but basically these percentages are basically to be compared to each other. I have never really understood what Nolan and Heinz wanted with the Cupid, but basically it shows a percentage, and percentages are just easier to compare within when you compare two different variables, because it relates them to the population. So if you have the calculation of a score from a percentile, we know that now, okay, so if we look for a percentile, we want to know how many are less than a certain value, or how many are within 63% of the population. You're interested in 63%. The way you approach this, again, you find on the distribution table the corresponding set score, and you again calculate back the score, the individual raw score. For the example of 63, it's considerably easy. So you can follow. These lines are basically continuous. So you go from 50, you go up to 60, you go to 63, that's 0.33. Okay, I can live with that. Let's do 0.33. So this is a set score of 0.33. For our example of the blood pressure, we have now 130 multiplied by 10. No, we have 130 plus 10 multiplied by 0.33. So that's basically 3.3. So we have 133. So we have 63% of the population are less than 133.33. So that's how you would approach this. And now we're getting actually to what, Michelle, you were interested in before. When you have individual levels, you can quantify and characterize populations. So essentially, the amount of people, the proportion of people in your population that have a blood pressure less than 133.3, as calculated before for 63%, is essentially 63%. So if you randomly draw now an individual out of your population, you have a 63% probability this individual has a blood pressure less than 133.3. If you're doing the same thing now with a distribution of means, you get a slightly different insight. And what does this mean? Okay, so I'm drawing a sample of 30 individuals from a population. I have 30 individuals from the population of New York, and I basically want to quantify another blood pressures. I measure 30 blood pressures, I get a mean, and I get a standard deviation from my sample. So I know now the mean of my sample. And I want to know now whether my sample is representative of the blood pressure in New York City, the average blood pressure in New York City, which was 130. In my sample, it's, let's say it's only 122. So I am now next interested, okay, in my sample, let's assume, based on my sample size of 30, I will have in my sample, for all these samples, if I draw a sample of 30, I have a probability that these sample means do have a variability, which is affected by the variability in the overall population. That means if you have a lot of variability in your population and you draw a random sample, your probability of having more variability in your samples is also going to be higher. Therefore, that distribution and that variability of your means will essentially be dependent on the standard deviation, on the variability in your population. And this is where the standard error of the mean comes in that we calculated last time, which is basically, where's the formula, which was calculated as standard deviation of the population divided by the square root of the n of the sample size. You remember that equation from the slide last time. So this means that, let's go back to that. That was actually a pretty good slide. This calculation is exactly that jump. You have individual scores that have a very wide variability. That's your population. If you only have interest in the means and the variability of the means rather than the individual scores, you are facing something that looks like this, because your mean estimate will be considerably less variable and will be a more accurate reflection of your mean than the individual scores. So these become slimmer, and this mean of different samples is more reflective of the population mean. That means here's the population mean. If you remember last time, the mean was around 5.382 or something like that, 5.3. So that's represented here by these individual scores. If I'm drawing now repeated samples and I calculate mean for each of my samples, and I have now 10 different means, all drawn from a random sample, this will have very little variability around the mean of all my sample means. So it gets slimmer. And the accurate of the mean of all these means, will essentially be very accurately reflecting that mean that you really see in your population. So going back to the blood pressure example, in the New York City population, I have now my sample of 30 people that I've drawn from the New York City population that has a mean. That mean may or may not represent the population mean. And I am now finding that out by quantifying this standard error of the mean. So we have the standard deviation in the population. We know how much variation there is in the population. And I know I have drawn a sample. And I am estimating what a sample of the size that I have drawn will show in expected variability. So I'm assuming I have drawn actually not just one sample, I have drawn, let's say, 100 samples. And I'm quantifying now, based on the standard deviation of the population, I estimate the variability of these mean estimates based on these 100 samples that I've drawn. That is what hypothesis testing basically has as an underlying assumption. And this is the central limit theorem, this relationship between a population mean and the distribution in the population and how this relates to the sample mean. Yes? Correct.
Therefore, like how accurate it is.
Correct. Correct. And what the probability is that this is actually significantly different or it's the same.
Like this small population.
Just my sample, yes.
Yeah.
And you're doing that by basically estimating the variability, the uncertainty within my mean estimate. That is what you're quantifying, really. Good. Standard error of the mean. Variability quantified as a standard deviation comes from the population. The more variability of that individual score of that blood pressure in my population will essentially increase the variability in my means because I'm drawing. So if there's more variability, there are more individuals that basically have these extreme values in my normal distribution curve. So I'm drawing here individuals out and I have a greater probability that I actually have values that are far away from the mean, which will affect the certainty of my mean estimate and will consequently also affect the certainty of being able to estimate that mean based on my sample. If you have a larger sample, and this is the numerator, right? That's just the sigma. That's the standard deviation. If you have a larger sample and your sample size is larger, let's say you don't study just 30 individuals, but you study like 500. What will happen if you have a larger number in the denominator? This will automatically counteract that variability, that increases that variability, and will make it a smaller estimated variability of these means. So we'll basically make this slimmer. So variability in your population makes that variability of your sample means wider, whereas a division by a larger sample size and a larger sample size studied or measured will make it thinner or slimmer. That is the standard error of the mean. And so now to your question, how does this all relate to the STAT scores? Because now we want to know, and this is where we're going back now to the hypothesis testing slide. We want to know now the slides are just not as great. We want to know, don't look there, stay with me. We want to know the probability of this mean actually being an accurate reflection of your population mean. And you're testing this by basically calculating, that's again in the other slides from last time, you're basically calculating this with this formula. You're calculating this again as a STAT score. But this STAT score has a different interpretation because it is basically the mean from my sample minus the mean, the mu, from my population. So I measured a sample mean and I have 30 individuals. I measure all their blood pressures, get those individual scores, 30 individual blood pressure measurements. I calculate the mean of 30 blood pressure measurements, and that's 122. And I'm comparing this now to my blood pressure of 130. That's 122 minus 130, that's minus 8, divided by my standard error of the mean. And the standard error of the mean is 10 divided by 30 because it's 10 divided by a square root of the square root of 30. Because the standard deviation is sigma is 10, we said. 30 is the sample size. It's square root of 30, which is, I don't know who has a calculator. It's basically, it is like somewhere in the realm of 1.6, I would think. So this STAT score is basically now a characterization, a standardization of the distribution of the means. And now taking this knowledge that we know from Manuel's height, if now in my standardized difference, so I standardize, what I essentially do, I standardize the difference between the mean of my sample and the population mean. So that's -8. And I standardize this by this assumed variability. So that is a constant, right? So this is always 130. And now I assume that this difference is being standardized. And by that, I find out whether my extremes are basically, if I define these extremes, whether my population mean is inside of these extremes or it's outside. And if it's outside, then it's significantly different. If it's inside, it's actually not significantly different. And the null hypothesis is true. Yes, please.
How do you find the extreme?
That's the million-dollar question. That's based on a probability that you're willing to accept to be wrong. That's the, so okay, now I'm going back to, I'm utilizing now the slides because these are just the better slides. Okay, so you make hypothesis testing to find out wrong versus right. So your null hypothesis is that your sample mean is not different from your population mean. Your research hypothesis is that the sample mean is different from your population mean. You have now the probability to be right or wrong. You can say, my sample mean is significantly different from my population mean. If that is indeed true, that extreme is gonna be a reflection of, it still could be from the same population, it still could be true, it just could be a random sample that I've drawn that is just a little different now. So that's the type 1 error, that I have a false positive where I'm saying, okay, so this is really significantly different, but I'm only certain with less than 5% or more than 5%. Or I make a type 2 error that I say there's no difference, but it was still a random sample and I still make a wrong decision. So that's actually a different probability. But these two possibilities exist when it comes to research hypothesis and null hypothesis. So research hypothesis, I'm rejecting something that I should not have rejected, leads to a type 1 error. I am not rejecting what I should have rejected, is a type 2 error. And this basically comes down to the following. Let's look at an example. Yeah, I'm skipping now the 6 steps of hypothesis testing. That's not good, but let's stick with those slides. Okay, so hypothesis testing. So this is what you essentially do. You mean to see whether the difference between your sample mean to your population mean is actually as large, or the variability is as small, that this sample mean is actually significantly different from your population mean. So you're testing this now. But first, in step 1, you formulate a null and an alternative hypothesis. So again, blood pressure example, I'm saying my blood pressure, or the blood pressure in my sample, is not significantly different, is not different from my population blood pressure, and or the mean population blood pressure. The research hypothesis is like my sample, the mean blood pressure in my sample is actually significantly different from the population blood pressure. That is writing it out, and you literally write this. That's important that you write it because that will help you to shape your thinking in that direction that you will have them right. So in the end of the day, okay, so this is a different example. Let's go away from the blood pressure. Let's take cholesterol. All of you have had a cholesterol measurement at one point in time. There are some certain thresholds which you shouldn't be over. If you are over, then you need to eat more fibers, or in worst case, you need to take a statin or some medication. We are now in our study comparing the blood pressure of smoking males compared to the general population. We know that in the general population, the mean is 211 milligrams per deciliter, 100 milliliter is the same. So I am now formulating a null hypothesis where I say my mu is the same as the mu zero. So mu here is the sample mean, mu zero is the population mean. Research hypothesis, HA, HO, HA. Research alternative hypothesis is that my sample mean is different from the population mean. Having this actually expressed in numeric terms, so mu, sample mean, sample cholesterol mean, sample mean cholesterol equals 211 milligrams per deciliter, or is not equal to 211 milligrams per deciliter. You can also, let's not do that yet. Let's not talk about this yet. So this is my test. And so the decision that I'm making is either it is different or it's not different. It's binary. It's either yes or no. Therefore, I have the risk of making type 1 error that I say that's different and it's actually not, type 1 error. Or I say it's not different, but it actually is different, type 2 error. Good. The type 1 error, where I actually reject the null hypothesis that shouldn't have been rejected, is quantified by that formula that we have seen, that STAT score. So this is mean minus my population mean divided by the sigma. No, not by the sigma, but the sigma divided by the square root of the n. So that's my standard error of the mean. So I'm taking this difference in the numerator and I divide it by my standard error of the mean, and I standardize the difference. And if the difference is in those extremes beyond a certain point, then I will reject my null hypothesis. And these extremes are defined by the acceptable type 1 error. What probability am I willing to accept to be wrong? And that is commonly 5%. This is set at 5%, and that corresponds with a STAT score of minus 1.96 and plus 1.96. And we will look in a second what that means. This threshold is defined by this 5%, can also be 10%, can also be 1%, depending on various use cases. But this is overall called the so-called significance level, alpha. So alpha corresponds to a type 1 error. So this is the calculation of how you're calculating this. So again, this is x minus mu, sample mean minus population mean divided by the standard error of the mean. And that is the so-called test statistics or STAT score. Well, it's not really a STAT score anymore. It is called a test statistic. It's an important distinction, actually. So what I actually want to calculate now, so this is now, let's think of the cholesterol example. I am essentially calculating a difference between a sample mean and a population mean, which is a certain value, a certain difference, let's say 16. And now I take a variability of these sample means that I would expect, and I'm using this variability because the population mean is not changing. That's just one value, so that's a constant. So now I utilize the standard error of the mean, the variability of these means, to standardize my difference. And that gives me now a difference of 0, which is the mean. That's what STAT equals 0. Or something more extreme. And then I define here those thresholds that are my extremes. And if it exceeds that extreme, then I will conclude this is different at a p-value that, or a probability that I am calculating, which needs to be lower than that acceptable type 1 error rate. So you're basically quantifying the probability of rejecting a null hypothesis that actually should not have been rejected. And if that probability is smaller than 5%, you're taking the risk, you're rejecting a null hypothesis. And you take a probability less than 5% of risk into account, that you say, I'm rejecting it, that's my decision. That's how I dichotomize my decision. So how do you do that? So we have seen the formula, right? So that p-value is basically nothing else but, again, calculation of a set score of a test statistic, a set. So that's -8 divided by the standard error of the mean, gets me a certain set. And what, and based on that set, I will now calculate a p, which I'm getting from the distribution table. And that basically will lead me, if that is smaller than the alpha, will lead me to rejecting the null hypothesis. Okay, I went over really terribly. Okay, have a nice evening.
So